You all, some of you are known to me for a long time and some are new faces. So, I profusely thank Angona and for her illuminating introduction, but best way to introduce me is that I am one of the ex-students of this department and Presidency College. That's all. It speaks of many things. When you become an ex-student of Presidency College or now Presidency University, then you are different from other students from any other part of the world. That's all. So we need that kind of confidence among us, and I am sure that you people will have the same feeling when you come out, and when you will be established in your life, you will have the same kind of feeling. Anyways, I am really grateful to the present day Geological Institute committee for inviting me to give this prestigious talk. Frankly speaking, to anybody who is an ex-student of this department, being invited in a sraymemoriallecture is a dream. And that's the highest reward one can expect from being a student of this department. So I am very grateful, and I think I am not really fit for this. But anyways, I will try to do justice on the responsibility what the Geological Institute has been bestowed on me. So, in one of these humid, this September afternoon, I also being introduced in this department in the very same room about 40 years back, a little over 40 years back. And my first class was taken by none other than another legendary professor, Professor Ajit Kumar Saha. And it gives me a great pleasure to come here again to talk to you and to exchange the ideas of scientific interest with you. And it also reminds me, during that time, in the year 1981 or 82, when I was just a first year, second year student, not knowing much about geology, there was another legendary professor of our times, Professor Ashok Mukherjee, who was also a great alumnus of this department and also a professor at the IIT Kharagpur, a very legendary professor of economic geology of all times. Professor Ashok Mukherjee was also a student of Professor Santosh Ray. I never saw Professor Santosh Ray because when I entered into this department, he already, he was no more. But I saw, and I being taught by the students of Professor Santosh Ray, and I know the test of teaching that we got from those teachers are actually the training of Professor Santosh Ray. So Professor Ashok Mukherjee on that very lecture uttered two words that I could remember till now, because the other things I could not understand because I was just like a first year student, but like some of you. He uttered that it's a pygmy's effort to garland the statue of a giant when he spoke about Santosh Ray. So I feel, now if Ashok Mukherjee, a teacher like Ashok Mukherjee says that it's a pygmy's effort, then what is my feeling now? I'm just nowhere. You understand? So, and the other word he uttered, I will come to that word little later. Anyway, let me begin my talk. So in the beginning, I express my gratitude to all the teachers of Presidency College of this department, and I have mentors, many mentors, among them Professor Anish Ray, who was the teacher here and who happens to be the son of Professor Santosh Ray, was a legendary teacher as well. And my supervisors, Professor S.K. Chanda, Professor Osru Chaudhuri, Professor N.J. Bukes, with whom I was associated for a long time. And I also acknowledge my long-standing collaborator, Professor Gautam Ghosh of this department, with whom I did lot of field work, and that forms the backbone of my research. And particularly on this topic, we could publish a paper, and so the collaborators on this research are my postdoc and doctoral researcher and my colleague, Professor Shankar Bose, who is here. And I must acknowledge the extensive support I received all along my life from Presidency College and Presidency University, and the grants I received from DST and all other different funding agencies, and particularly my present employer, IISER Berhampur. So with this, let us come to the topic. Now, you know, evolution of early atmosphere is a very important issue for not only for the earth scientists, but also for the biologists, because it is intricately related to the development of life and to the proliferation of life. And in this field of research, there are a few pioneering scientists who made path-breaking discoveries and who strengthened the hypothesis for the early evolution of the atmosphere. So, of them, these 4 persons, Professor Preston Cloud, you know all of them, he was a geobiologist, paleontologist, who worked on the early life and the origin of life. Professor Henrik D. Holland, he was in the Harvard University and Princeton University. He was also a pioneer work and proposed pioneering hypothesis on the atmospheric evolution. And I must say that I had a very rare chance to spend some time with him, and he told me very interesting stories. He told me the name of 2 of our teachers here, Professor Ashok Mukherjee and Professor Aniruddha Dey. You don't know, but you know all of my colleagues here, they know these 2 teachers. Professor Aniruddha Dey and Ashok Mukherjee were his postdoc fellows at the Harvard University. So I was quite delighted when I was with him and he was talking about Kolkata and these 2 people whom I know. Then Hiroshi Homoto, another American, you know, of Japanese origin. He was actually a student of Henrik Holland. He was also a big contributor to this field. And Professor Nick Bukes, my mentor for the postdoc fellowship and my long-standing collaborator, and he made seminal contribution in this particular topic. So without mentioning these names, this topic will not be covered adequately. So let me give you the outline of the talk. So I will briefly introduce this problem, and now I will say this word, non-uniformitarian world. This term I first listened from Professor Ashok Mukherjee's lecture during my first year class, and I had no idea what was the term, but it remained very catchy, and I could remember for a long time. But when I started my research, particularly in the late career of my research, I realized the significance of this term. Non-uniformitarian world is the world which was never before like this. So whatever the processes that took place during the early days were completely different from what the processes we are seeing now. So most of my research are on these unexplored or unseen processes which are completely different from present day world. That's why non-uniformitarian concept is very important for those who work on the Archean and Precambrian rocks. Then I will cover the evidences in favor of reducing state of atmosphere, mainly field and petrography, stable isotope proxies, then chemical signatures. Then I will talk about great oxidation events and the evidence from oxic paleosols and some isotope signatures. Then some new ideas that fine-tuned the concept already prevailed, and how the Indians can become an important contributor in this whole exercise. That I would like to highlight. So what is the problem? Problem is that there are 2 school of thoughts. One led by Hiroshi Homoto and Dimroth Schobel. They think that the Earth's oxygen concentration of the atmosphere was very same at that time what it is now. That means 100% PAL. PAL means present atmospheric level. If the present atmospheric level oxygen is around 20%, Hiroshi Homoto and Dimroth, they suggested that it was like that throughout the history of the Earth. But the other group, led by Preston Cloud, Walker, Custing, and Holland, they said that no, the atmosphere was completely different. and it was essentially reducing and anoxic at least until 2.3 billion years ago. And suddenly there is a jump of oxygen concentration, and gradually oxygen concentration reached to the present atmospheric level at a very late time. So these are the two distinct school of thoughts on the oxygenation, or history of the oxygenation of atmosphere. Now, let me discuss what are the evidence in favor and against. So, let me discuss first the evidences in favor of reduced atmosphere. So, there are several evidences, several lines of evidences covering different aspects of geology to record that the atmosphere was anoxic and reducing in the beginning. Like from the field observations and the lithology, the detrital paleoplacers, that means the sediments, they contain some detrital redox-sensitive minerals like uraninite and pyrite that suggest that the atmosphere was reducing at least before 2.2 billion years. Then there are evidences of paleosols. Some of the paleosols are reduced in nature. That means they could not retain the iron oxide. And then mass-independent signature in the sulfur isotope fractionation. That's a very smoking gun for the reducing atmosphere evidence. And redox element distribution of uranium and molybdenum in the ocean sediments. So these are the few lines of evidence that supported the reducing nature of oxygen in the rocks which are 2.2 billion years or older. So I will show you one after another these evidences. So this is the field photograph of paleoplacer. You know what are placer deposits? Placer deposits are sedimentary deposits that concentrate some of the economically important minerals because of their high specific gravity. You know that the gold placers are there close to our own state, Suvarnarekha. The name of the river is from the gold placers. So similarly, we have diamond placers, and the reduced paleoplacers means they have the reduced element, reducing minerals that are not stable under the present day atmospheric oxygen concentration. So what are those minerals? Mostly the uraninite. There is a rock called quartz pebble conglomerate that contains the tiny little uraninites, and our atomic minerals directorates, there is a division who are prospecting for those detrital placer uraninite deposits, but where they will find on those rocks which are at least older than 2.2 billion years. So that's why we call them reduced paleoplacers. And along with the uraninite, they can also have pyrites. If you leave pyrites in present day atmosphere, it will be rusted. What do you mean by rusting? So So pyrite will be totally oxidized to goethite. So it will not be stable. It can only be stable if you put it in a reduced state, reduced atmospheric state. And those rocks which are deposited before 2.2 billion years, they were in the reduced state of atmosphere. That's why the pyrites were stable. So these are the pictures from our own rocks in the Mohagiri Hills in southern Shingbhum, the detrital uraninite and pyrite paleoplacers. They are being prospected by AMD. And you see some of these photographs, ACM photographs of uraninite that we took here at Presidency College ACM lab, the first ACM that we procured here in the year 2007. In that ACM, we took the pictures of this reduced paleoplacer of uraninite and pyrite in this very room there. And this is one of these detrital uraninite image also captured in Presidency University ACM, Presidency College to become university during that time when I took this picture. This is one of the best photographed detrital uraninite in the world. So its roundness and the outline suggests that it has suffered the sedimentary transport. That's why it became smooth. Otherwise, it would have very sharp crystallographic edges. That means when this rock was deposited, the atmosphere did not have sufficient oxygen so that the uraninite was not dissolved. If there were a lot of oxygen, then this uraninite, which is now in +4 state, would have been converted to U+6 state, and U+6 is a soluble state of uranium, and it would have been totally carried away by the groundwater. But it did not happen. So Mahagiri quartzite was deposited during a time when there was very little oxygen. What was the measure of oxygen? 10 to the power minus 5 pal. That means oxygen was 10 to the power minus 5 less in concentration than present day atmosphere. So you can imagine, it's 0.0021% of oxygen was there. So can you imagine what was the condition of the earth? Could you survive? Could you survive in 10 to the power minus 5 pal oxygen concentration? You will suffocate. Or otherwise, you must have developed some other kind of mechanism for metabolism. Now the next line of evidence comes from the paleosols. Do you know what is a paleosol? Paleosol is an ancient soil that is preserved in the rock record. Who all of you do not understand what is paleosol? You can raise your hand. From first year students? Yeah, very good. I'm very glad that you don't understand. You know, have you seen soil in your life? Yes, if soil is here in our ground, there is a soil. Now imagine after say 500,000 years from now, 5 lakhs years from now, what will happen? What will happen to the condition of this place after 500,000 years down the line? Any idea? You can say. What will happen? Yes, it will be covered under Bay of Bengal because of the global warming. So the soil will be covered by the marine basin, ocean. So what will ocean do? Ocean will deposit sediments. Ocean will deposit sands and carbonates and limestones and all that thing. And if this soil that we have, set up here with spending lakhs of rupees, touching crores of rupees here in Presidency College football ground, if it can survive the rigor of the wave actions of the coming marine incursions, then part of this will be preserved and it will be encased within the new sediments. So maybe after say 20 or 30 lakhs years from now, the sea receded. I will not be here, but some of you may be there. So if you come here and if you put a drill there, then you will find that yes, Presidency College football ground soil is still there. So that's a paleosol. Okay? So the scientists actually discovered similar paleosols in some of these places. In Western Australia and in Southern Africa and Canada. And one paleosol also in India. So what is the age of these paleosols? The uniqueness, they are much older than Presidency College paleosol. What is the age of these? Some of these are 2.9 billion years old. You know what is 2.9 billion? Do you have any idea? 2,900 million or 290 crore years old. And our soil is only 5 years old. And then this is a paleosol which is around 2.2 billion years. And these are around this is also 2.2 billion years. So we have an array of records of old soils that we can study. Then what is the reason? Why should we study paleosol? What is the great about it? What is the great about it? Why should we study paleosol? Any idea? Any idea? Any idea? No teacher, please. Any idea? How? How do you know? No. So soil is in direct contact of what? Air. If the air has oxygen, then the soil will have some signatures of the oxygen. Now what is the signature of the oxygen in the soil? What it will form? What oxides? What oxides are there in the soil? Do you know? Can you name any oxide which is in the soil? SiO2 was not from atmosphere, it was already there from the mantle. Which was there, which oxide is there in the soil by which it is being, Yes, very good. What is the name of the iron oxide that caps the soil? What? Yeah, ferric oxide is the chemical name, but what is the name of the soil that contains the ferric oxide? Very good, you are intelligent. You are Presidency College, Presidency University students. So you will have laterite. So it is a direct interaction between the atmosphere and the soil. And if the soil had oxygen, then it's very easily you can see that it's a laterite capping. So once you get a paleosol with a laterite capping, can you identify laterite? Do you know what is laterite? Have you seen laterite? Yes. If you go to temple of, Jagannath temple in Puri or anywhere in Orissa, it's full of laterite bricks. If you go to western part of our West Bengal, Purulia, Bankura, they're all landscape is full of laterites, soil. So we are all very much acquainted with laterite. So if you find a laterite in a rock which is about 1 billion year old, that means atmosphere was fully oxic to produce that laterite. That's the direct evidence. So next time when you go to the field, you will search for paleosol. How would you search for paleosol? How do you know that's a paleosol or not? Do you have any idea? What is a soil? Soft and slippery. So it is made up of lots of aluminosilicates, alumina. So soil will be rich in alumina. Okay? Alumina-rich minerals. Why it would be rich in alumina? Why the soil would be rich in alumina? Huh? Yes, because alumina is the most stable. In chemical weathering, the end product is bauxite, Al2O3 rich, and then laterite and bauxite. So anything rich in alumina, you should try to see whether it is a paleosol or not. Now if it is being metamorphosed, then what would be the nature of that alumina? What will you get there? What mineral would be rich there? A metamorphosed paleosol, how do you identify? With a metamorphic mineral that has contained only alumina. What is that? A metamorphic mineral which is rich in alumina, essentially with only alumina. Huh? What? Yeah? Limonite is not alumina. Limonite is iron oxide. Huh? Only alumina rich. You have already drawn those phase diagram, triple point, so many things you have calculated. Huh? Kyanite, sillimanite bearing rocks. So if you see in the metamorphosed horizon, there are some layers of kyanite and sillimanite. You must explore that whether it's a paleosol or not. And if you get the aluminosilicate rich layer, which is as old as 3 billion year old, then it's a paper in nature. You understand? It will pay all your expenses throughout we have taken from the government. Okay? We will come to that. And these are the images of how the paleosol look like. It's very difficult unless some of them are very difficult, some of them are quite easy. But this is the Hekput paleosol, which is 2.2 billion years old. So it is developed between the layers of basalt. It is in South Africa, close to Johannesburg. And this is our own Keonjhar. You know this place called Keonjhar? You have been there? It's very close, 300 something kilometers from Kolkata, you go there, fantastic place. And there is a village which is very close to Keonjhar called Madrangi Jori. There you can have this fantastic section. What is there in the bottom? It's a weathered granite. And why they are mining it? It's a mine, open cast mine. Why they are mining it? Because this weathered granite has a very soft feeling of talc. So they mine it for talc powder. So if you buy a talc powder with a price say 200, 300 rupees in a fantastic, foreign made pack, this pack and that pack, actually it comes from the poor paleosol, and you are buying it with 5,000 rupees or something like that. You are putting the paleosol on your face and you look good. But the story is, you have to come to the geologist to identify what is talc and not. Okay? So, now, it's not only that when you get aluminosilicate or this aluminous rocks, rich layers that are all paleosols. Alumina can also be concentrated in some other processes. What are the processes that can concentrate alumina other than weathering? Any idea? Any idea? You forgot. When I give a hint and they will jump up. Huh? So, you know the hydrothermal alteration? So if you have a lot of hydrothermal alteration, then also you can leach some of the mobile elements from the rock and you leave behind the alumina. So it can have alumina carapace of alteration if you have some alumina-rich rock. So it is difficult. But in chemical study, if you now take the soil from here, then you will see that some of the elements are not changing. This is bedrock. So these are very immobile elements like zircon, titanium, and aluminum. So these are not changing. So their composition will remain as the same as the bedrock. What will change? The change will take place in the alkali metals and alkaline earth metals like sodium, potassium, magnesium, calcium, because they are not stable under weathering conditions. You will see depletion of these elements with respect to the bedrock. Then you will understand that this is a horizon which has suffered a lot of leaching because of weathering. It can be a paleosol. And most importantly, the iron. Now, iron concentration is crucial to understand whether it is oxic paleosol or reduced paleosol. Why? Because, iron in reduced state, if it is in +2 state, then iron is soluble. If it is +3 state, iron is insoluble. So if your atmosphere is in reduced state, then whatever iron you have, they are soluble and they will leave the place. The soil cannot retain the iron at all. So you will not have any laterite if you have a reduced atmosphere. So your iron will show consistent depletion. But if it is an oxic paleosol, then you will have a capping of iron at the top. Okay? So these are chemical signatures by which you can distinguish the paleosols of different environment. So this is an example of reduced paleosol from one of the best studied paleosol horizons of Western Australia, Mount Roe paleosol. And this paleosol is developed in between basalts, in the basalt flow of basalts. Do you know basalt flow? Have you seen any basalt flow? Do you know of any basalt flow in India? Deccan Trap. Have you seen Deccan Trap? No. Some of you must have seen. In between some of these traps, what we have? Intertrapians. Very good. And other than intertrapians, we also have one thing called red bowl. That means the red soil. So some of our Deccan traps in between the flows also developed some lateritic soil, which have the red capping, because the Deccan trap was developed at what time? 65 million years or 64 million years. So atmosphere was fully oxic. That's why it developed red bowl. But this Mount Roe paleosol, when it was developed in 2.7 billion years ago, there was no oxygen. So it did not form any red bowl. What did it form? Instead of red bowl, what will you call in between the basalt flows? It has soil, but not red bowl. What will you call? What would be the color? Yellow will have, if you have limonite, then it will be yellow. If you have nothing, no iron, gray bowl. So it's not red bowl, it's gray bowl. You have to think, you must have a simple thinking. Geology is not very difficult. You have to conceive. Every step, you have to correlate. From here to Australia, from here to South Africa, what is there? You have to correlate across the ages. If this is the red bowl, then if the soil is there in 2.2 billion years, what would be the color? And if you have this clear idea, then when you go to the field, you will be able to identify what is there. Okay? Otherwise, you will ignore and go away with your Jeep vehicle, air-conditioned vehicle. In our time, there was no air-conditioned vehicle. So it was an old Jeep, old-fashioned Jeep with cloth, and I know Bimala had a lot of experience, much more than I have. I had little experience while doing field work in ISI. We used to carry these old Jeeps with trailer and camping materials, and those days were fantastic days. A camping geologist's life is a fantastic life. Okay? Now we come to a little difficult evidence that is called isotopic, stable isotope evidence. So what is that stable isotope evidence? You know, some of you are not introduced with the stable isotope systematics. So for them, this is the introductory slide. So for example, sulfur. Sulfur has 4 different types of isotopes. And you know, the most abundant isotope is sulfur 32. And other isotopes are 33, 34, and 36. Now what happens? When the sulfur takes part in any equation, any reaction, then there is a fractionation between reactants and products in the ratio of their isotopes. That's called isotopic fractionation. And this is the equation by which you can estimate the isotopic fractionation. Now, I'm not going to detail because there is not much of time. Thing is that delta 34S means you are measuring the fractionation between 34 and 32 sulfur. And when I say delta 33, that means you are measuring delta 33 and 32. So in the same sample, you can have multiple sulfur isotope signals. You can have delta 36 isotope signal, delta 33, and delta 34, all measured against delta 32. Now, why do you need this? Now, if you do the multiple sulfur compositions from a particular rock, then you will find that there is an empirical relationship between the fractionation of delta 33S and delta 34, or delta 36, or delta 34S. So, it's a y is equal to mx equation. So, this is the slope, this is the constant. So, this is called mass-dependent fractionation. That means whatever fractionation will take place, if you know the value of delta 33, you can calculate the value of delta 34. Is it clear? Is it clear? If we think that fractionation is mass dependent, and if we know the mass dependent constant, then it is possible to know without analyzing, without spending more money, that if I get delta 33 value, I can recalculate delta 34 and delta 36 values. Is it clear? Any doubt? Okay, this is called mass-dependent fractionation. Now what happened? Why it is important? Now, if you go to those days when there was no atmosphere, then they studied the sulfur from pyrite. Pyrite is a mineral that has a lot of sulfur, and pyrite is very abundant throughout the geologic record. So you can collect pyrite and analyze. So when they analyze pyrite, they see that this relation doesn't hold true. Why is that? Because they are not following this linear equation. They are not following this 0.515 constant. They are totally not correlatable. The two parameters are not correlatable. That means the fractionation did not take place in a mass-dependent way. So they call it mass-independent fractionation. So all the pyrites measured, which are older than 2.2 or 2.3 billion years, they show that this relationship is not true. Why is that? That is because they then did some experiments. That is because the fractionation rate in the isotopic reactions are controlled by some electromagnetic radiation of a particular bandwidth. What is that bandwidth? The bandwidth is ultraviolet bandwidth. So in the ultraviolet bandwidth of electromagnetic radiation, if the isotope is subjected, then the mass-dependent relationship is totally destroyed. So it is because of the ultraviolet ray, that's why the sulfur of the pyrites, which are older than 2.2 billion years, they are not actually following the mass-dependent trend. And why UV rays are coming? Why UV rays are coming and attacking the pyrites in the terrestrial sediments? Any idea? Huh? Why? Very good. There was no ozone layer. That's why UV ray could come and mingle the isotope reactions. Why there was no ozone layer? There was no oxygen. So how to polymerize oxygen and develop ozone? So that's a telltale evidence that there was no oxygen during that time because of these mass-independent isotope signatures. So there is an example from the pyrites of 3.8 billion years, the oldest sediments recorded on the earth, and it shows that mass-independent fractionation. This is the mass-dependent band, and the plots are here, way above this mass-dependent band. So most of these ages are like that. Then, so we have covered evidences of sedimentary evidences of paleoplacer, detrital reduced paleoplacer. We have covered the evidence from reduced paleosol. We have covered evidences from mass-independent isotopic fractionation. 3 evidences we have covered. Now the 4th evidence is, which comes from the oceanic sediments. If you analyze the oceanic sediments through ages, you will see some spikes in some of the elements, like uranium. You see that there is a spike in uranium concentration right at around 2.2 billion years old. And then again, uranium is very high above in the sediments which are younger than 600 million years. Why is so? Why uranium is suddenly high here and high here in the marine sediments? Any idea? Any idea? Why uranium is high in the marine sediments? Any idea? I have given the clue for this question while I was discussing the uranianites. Huh? What? Yes? Yes, very good. If the atmosphere had a lot of oxygen, then the uranium from the crust will be weathered and dissolved in the water and transported to the ocean and will be deposited in the ocean. So oceanic sediments will be richer in uranium during the oxygenic atmosphere. So there is a spike in oxygen concentration at that time, and there was no spike here. And then again a dull period. You know what is this period called? 1.8 billion years to 8.8 billion years? Very good. Boring billion years. And the ocean is called? Do you know the name of the ocean during this time? It is called Canfield Ocean. Don Canfield. Don Canfield from city of Copenhagen. He first proposed this reducing atmosphere and boring billion during that time, 1,000 million years ago. So oxygen actually fluctuated. So to sum up everything, all the evidences, there is a curve that gives rise to the idea that the oxygen was minimum up to till 2.4 billion years ago, and there is a certain spike in oxygen, and then there was again low standard, and then again little bit of oxygen to touch the present day condition. So this was the summary curve which was reviewed by Timothy Lyons in the year 2014. It's a Nature review paper. So you can download this paper. It's an excellent paper that sum up the development of oxygen in the atmosphere. Now, when did the atmosphere become oxic? What is the evidence? So far, we were discussing about the hellish atmosphere. Now, let us discuss about the more greener atmosphere, habitable atmosphere. When the habitable atmosphere first appeared, again it comes from the Heckwood Paleosol. The Heckwood Paleosol 2.2, that means Paleoproterozoic Paleosol, it developed again within the basalts in parts of southern Africa, from South Africa to Botswana. You know the country Botswana? Why Botswana is famous? Can anybody tell us? Why Botswana is famous? Where is Botswana? Where is Botswana? Huh? Huh? Very good. Why it is famous? Why it is famous? Very good. And money? What is the money, source of money? No, don't be so cruel. What is the source of money? Not only gold mines, diamond, the kimberlite pipes, diamonds forever. They mine from Botswana. So what is important here, in one of the drill codes from Cameroon, they discovered the laterites. And on the top of this soil profile in between the basalt, suddenly there is a spike of iron. And this is the oldest laterite so far discovered. And this is the turning point when people used to think that oxygenation took place between 2.4 to 2.2 billion years. And then, how do you constrain the time? They also constrain the precise time for oxygenation. Again, they got some drill cores from some parts of the Transvaal mountain chains in South Africa, and then they found the exact turnaround from the mass-dependent to mass-independent, mass-independent to mass-dependent fractionation. So that turnaround gives an age of 2.33 billion years. So 2.33 billion years is now known as the exact date of Great Oxidation event. So this is again the profile in detail and the curve showing the mass-dependent fractionation in sulfur isotope from the same section, from where the exact date of, precise date of Great Oxidation event has been measured from some parts of South Africa in the Transvaal mountain chains. Now what is important? It is important that how the atmosphere became oxygenated. So this was the pioneering idea of Preston cloud. I showed you the picture of Preston cloud. He was a legendary professor of University of Santa Barbara, University of California, Santa Barbara, and he was a professor of paleobiology. So he proposed that the distribution of banded iron formations throughout the ages is a clue for the oxidation of atmosphere. Why is that? You know, the banded iron formation distribution, if you follow, there is a peak. There is a peak of banded iron formation distribution at around 2.5 billion years. Where are the maximum development of banded iron formation? It's in the Hammersley Basin. Where is Hammersley Basin? Where is Hammersley Basin? Delage Gorge members? Where is that? Any idea? The biggest iron ore mines are there. Yeah, you should know. Hammersley Basin is Western Australia, near the city of Perth. Okay? There is a spectacular development of banded iron formations of 2.4, 2.5 billion years. And the same banded iron formation of same age is also developed in the Transvaal mountains in South Africa. And people used to think that Australia and South Africa were close together. And they used to call that Bhalbara Creton, Pilbara and Transvaal. So it's a continuation of banded iron formations. Now what is the importance of that? So huge banded iron formations deposited during the transition between 2.4 to 2.2. That means whatever little bit of iron was stored in the ocean were all oxidized by little oxygen that was produced by the cyanobacteria, and it consumed all the oxygens, and iron oxides were Fe3 or Fe2O3 was formed, and that gave rise to huge thick banded iron formations. When all the iron in the ocean was exhausted, then only the oxygen can come out and can oxidize the atmosphere. So distribution of banded iron formations are very important. Do you know where we have the banded iron formations in India? Do you know? Do you have any idea? Huh? Bailadila, very good. And we have huge resource of banded. I will come to that later on. I will show you why it is important. Now, this is a generalized pattern of oxidation of atmosphere. Now, where to go? Now there is renewed research on some of these sections, produce new data, and that's the way forward we should look. What is that? So they recorded pre-GOE fluctuations. There are episodes of oxygenation before the Great Oxidation event. Then there are also post-GOE fluctuations before it became stabilized. And then there are oxygen oases in the oceanic oxygenation in the oceans. So what are the evidences for early surficial oxidation before the GOE? So it came from the Pilbara Paleosol, it came from the Nuze Paleosol, and it came from the Keonjhar Paleosol of India. What are those evidences? So these evidences suggest that there are spikes of oxygenation in between 3 billion years and 2.4 billion years, revealed by some of these evidence, some of these deposits. And then the new term, whiffs of oxygenation, came into being. So there were whiffs of some sudden rise of oxygenation in between. And it was proposed by none other than Professor Ariel Anbar of Arizona State University. So in favor of the whiffs, they analyzed again the data of the uranium with respect to total organic carbon and saw some of the spikes of uranium concentration in the marine sediments that are similar to GOE spikes. So that supports that there were several episodes of oxygenation before the main oxygenation event. Similarly, they also reassessed the molybdenum ion concentration in the shells, marine shells, and also noticed the same kind of spikes in the shells which are about 2.8 or 2.9 billion years old. So, now the question is whether it is a whiffs of oxidation, great oxidation event, or great oxidation transition. Is it a single event or a transition event? So that is now being the hot topic of research, and these two gentlemen, Professor Andre Baker and Professor Timothy Lyons from University of California, Santa Barbara, they are now actually pioneering this field of research of transition of atmospheric oxygenation during the Neo-Archean to Paleoproterozoic. So we have some contribution in this direction. We studied the Keonjhar Paleosol sometimes in 2014, which is developed on the 3.29 billion years TTG basement of the Keonjhar granite, and this is the Paleosol, and this is a sandstone. So you see the Paleosol is developed between a solid rock, between two solid rocks, and this is the talky Paleosol horizon. So we did some chemical analysis, and we found that the evidences are in favor of a Paleosol. So the iron was depleted, manganese was depleted, uranium was also depleted. The mobile and immobile elements give the steady amount, and also the the alkali elements and alkaline earth elements, they are also showing depletions. So this gives that these horizons are actually representing the Paleosol. We also did some of these rare earth element analysis, and interestingly we found that the Paleosols are showing negative cerium anomaly, and this is the granite, Keonjhar granite cerium anomaly, which is not negative, which is the bedrock, but the soil has a negative cerium anomaly. Negative cerium anomaly means the rare earth element is fractionated. That cerium is fractionated from other family of rare earths. That means cerium can only fractionate if you have little oxygen in the atmosphere. So cerium was oxidized and it was retained in the upper part of the soil, and in the lower part of the soil you see the depletion of cerium. That means presence of oxygen is indicated by the fractionation of cerium concentration in the Keonjhar Paleosol. So the model is like that. If you have a oxidized Paleosol, in the topmost part the Fe and amine will be enriched, and in the saprolitic part, that means in the weathered part, you will have depletion of Fe and amine, and this will be the complementary signatures of rare earth element distribution. So in the weathered part, the cerium will be depleted. In the oxidized part, cerium will be enriched. So in the Keonjhar Paleosol, we are having this signature. That means it must have been fractionated by the presence of oxygen. Then there are several other very recent proxies that were developed to study more advanced techniques used for the study of some of the Paleosols. So they used the chromium isotope, molybdenum isotope, iron isotope, and surprisingly, thallium isotope, which is which is available in the rock in a ppb level, but they have been able to measure that. So this is the Nuze Paleosol, another Paleosol which is about 3.29 billion years old from southern Africa. So they measured the chromium isotopes of the Paleosol and the lateral equivalent were the banded iron formations that are developing in the deeper part of the basin. So in the shallower part, the exposed part, Paleosol was forming, and in the same marine basin, deeper part, the iron formations are forming. So that they measured the chromium isotope from the Paleosol and also chromium isotope from the deeper part of the marine basin. And what they found? They found interesting results that these Paleosols are depleted and these BIFs are enriched in chromium 53. So when chromium is being oxidized, it becomes chromium 6. So if you oxidize chromium in the Paleosol here, then it will be transformed into chromium 6. And chromium 6 will take the heavier chromium isotope. So when it comes to the BIF will be enriched in heavier chromium isotope. That's how you see the chromium isotope is enriched here. And the Paleosol will be left with negative chromium isotope. So chromium isotope will be depleted here. You can see that the chromium isotope value is depleted here. So Nuze Paleosol, on the basis of the chromium isotope, they inferred that the Nuze Paleosol is also a oxic Paleosol. And this is the global chromium isotope record. And you can see that the maximum spike in chromium isotope is at around the Cambrian boundary. So that is the maximum development of oxygen in the atmosphere. Then there is another proxy from the same locality. What is the source of the oxygen? So they were trying to figure out the source of the oxygen. So what is the source of the oxygen in marine environment? Any idea? What is the source of oxygen? What? Photosynthesis, cyanobacteria. Then we need to know when the first photosynthesis took place. So that was also traced with the help of molybdenum isotope. So you must be very much upset that these are all difficult isotopes you are talking about. But they can give you amazing results. So you know the molybdenum isotope, when in the manganese oxide, if you go to the oceans, you will see the manganese oxide is now precipitating at the bottom of the ocean. And in the manganese oxide precipitated at the bottom of the ocean, they will enrich, they will take up the molybdenum isotope, the lighter molybdenum isotope. And if you have manganese oxidation in the surface, then the molybdenum in the ocean will be fractionated. Some of it will go to the manganese oxide that is being settled in the ocean floor. But for oxidizing the manganese, you need free oxygen. And to have this free oxygen, you must have photosynthesis. So the molybdenum isotope fractionation record suggests that some parts of the ocean were already having photosynthetic oxygen, which are now stored in the molybdenum isotope record in the manganese. The second thing came from the iron isotope. Iron isotope is important in understanding the iron sequestration in banded iron formation. So I'm not going to detail into iron pathways, but you should know that there are two pathways: oxygenic photosynthesis and anoxygenic photosynthesis. Oxygenic photosynthesis means the oxygen photosynthesis releases oxygen, and that oxygen is oxidizing iron, and iron oxide is precipitated in the BIF being oxidized. Anoxygenic photosynthesis, there is no oxygen. The bacteria actually takes out the electron from the Fe2 in the solution and oxidizes it, and it is called anoxygenic photosynthesis. Now, how to distinguish between oxygenic and anoxygenic photosynthesis? If you analyze the iron isotope, then there is a value which is closer to 0.75 or more. They are actually anoxygenic photosynthesis. So anoxygenic photosynthesis can create heavier iron isotope value, while the oxygenic photosynthesis can create little less heavier. So if you can measure, these are the values they measured from the Aquileia and the Greenland, the oldest BIF deposits in the world. So they get the anoxygenic photosynthesis signature. So many of the BIFs, which are actually oxide, very old, without any free oxygen in the marine realm, were oxidized because of the bacteria, because of the bacterial uptake of electron from the Fe+2 to produce it to the Fe+3, and Fe+3 was precipitated. So I'm not going to this more complicated thing because of lack of time. Let me come to the Indian scenario. So in India, we are in advantageous position if we want to study the oxygenation of atmosphere. Why is so? You see, the Kabul Craton in southern Africa, the BIFs are 2.5 to 2.1 billion years old. If you go to Western Australia, they're the same. The BIFs are only 2.5 to 2.1, and they are deposited in a very stable platform environment. There is not much of variation in environment of deposition between the BIFs of the Transvaal and BIFs of the Dulles Gorge member in Western Australia. But what is in India? If you study Indian BIFs, Indian BIFs are very easy to locate. Why? Why very easy to locate? Any idea? Why BIFs are important? Who says? Iron ore, because BIF gives money. Because BIFs are the money earners for our country. So most of the huge iron ore deposits are all hosted by BIF. So if you locate the iron ore deposits, you will locate the BIFs. So if you now look at these deposits, then you will see the BIFs are actually ranging in age from Paleo-Archean to Neo-Archean. So all ages of BIFs are there in India. If you go to Dharwar Craton, if you go to Bastar Craton, if you go to Shinghung Craton, if you go to Bundelkhand Craton, all over these Archean greenstone belts, they contain huge amount of BIFs. But not only that, and they represent a varied depositional environments, starting from the active continental margin. What is active continental margin? Active continental margin to passive margin. What is passive margin? Is our coast, east coast is a passive margin or active margin? Very good. Our Andaman coast is active or passive? So if you go to Chitradurga or if you go to Baba Budan, you will see both. Baba Budan has a coastline very similar to our east coast or west coast. If you go to Chitradurga, you will see again some of these margins are very similar to our Andaman margins. So we have all different types of depositional setting. If you go to Noamundi or Western IOG, you will see that it's actually very similar to our Western Indian margin, stable platform. If you go to Eastern IOG, then you will see that it is like Andaman Sea, or if you go to Southern IOG, it's also different. So we have a varied depositional setting for the BIFs. What does it mean? It means that the BIFs were deposited in varying depth. Some of them were deposited on the shallow shelf. Some of them were deposited in the deep ocean. Then some of them must have been deposited due to oxygenic photosynthesis in the shallow shelf. Some of them deposited because of the anoxygenic photosynthesis. So if you can study the iron isotopes from the BIFs from different regions, you can study whether the oxygenic photosynthesis was there during the Chitradurga time or not. If you get the signatures there, then you can say that actually the oceans became oxygenated way back in 2.7 billion years old. What is the age of Chitradurga Greenstone Belt? Any idea? Do you have any idea about Dharwad stratigraphy? Very, very awkward question. So I'm not going to embarrass you anymore. Now, our research has recently also discovered a new data, also generated new data on Western IOG. Our detrital zircon ages from the Western IOG is suggesting that Western IOG is about 2.7 billion years old. That is not older than 2.7 billion years. We used to think it's much older, but now this detrital zircon from sandstone patches within the lower shell of the Western IOG give us a data of 2.7 billion years. That means the Western IOG is one of the best candidates in the world to study the Neo-Archean development of the oceanic oxygenation. So if you can study here, then you will be able to understand what is going on. Very few places in the world that has this window unaltered. So this will be open to you. Some of you might take up this research during your PhD or during your research career. And I also give you some of the inputs that this is the banded iron formation from the Western IOG. These are tiny hematites within chart, that means quartz. These are platihematites. These all are platihematites from the same BIFs. And you see here, what is this feature? Can you tell us? Can you tell me what is this feature? This is a thin section photograph. What is this feature? Can you tell me? Any idea? You don't need to know a lot of geology. Tell me what comes into your mind. What is this white patch? What is this doing? What is this white patch doing? Any idea? It is breaking the upper lamination in brittle condition or ductile condition? Ductile condition. So it has developed during the very early stage of diagenesis, when the rock has not been solid. So then the pore water and these minerals are magnetite. So this is the water escape structure that comes from this part. It actually drains the iron and it deposited magnetite here. So what was there originally? Initially it was something else, and then it was reduced and it came with the pore water and deposited magnetite. So what was originally? Originally it must have been hematite. That means +3 iron, which were originally present in the sediment. That has been subsequently, during reducing diagenetic conditions, transformed into magnetite. So what does it say? It says that the bottom water of the Western IOG must have been oxygenated at that point of time. So this is a clue which you can work on. So these are the reactions that actually give rise to this kind of features. Like I'm not going into detail, but it can be done by redox reaction. It can also be done by non-redox reaction. That means excess Fe+2 and Fe3 can also drive these equations. Now what is this? The well-constrained drill core samples. We need what? We need well-constrained drill core samples because surface samples are all oxidized. So we need drill core samples to study this. So what is the advantage of India? India's advantage is very well preserved record of BIF from greater than 3.5 to 2.5 billion years. Wide span of depositional settings from stable platform to active margin or even ocean basin floor. Big mining companies capable of providing deep drill cores that go beyond the present day deep supergene weathering carapace. And we need capacity building in non-traditional isotope mass spectrometry. We need to develop labs. And my dream is, why not in presidency? We have enough space. We have enough training. A little bit of consideration can develop this department into really a non-traditional isotope mass spectrometry department. How much money we need? not more than 10-15 crore. And we have, don't laugh. No, you know what you have to try. You have space there, huge space. You can develop a lab there, have a dream. Unless you have a dream, you cannot go anywhere. So I think I really want to see, before I die, that this department has an excellent mass spectrometry laboratory somewhere in the swanky campus that we have built in Rajarhat. Okay, don't tell it to the administration, then I will never be allowed to come inside. But keep the dream and try for it. It's not big money. We got 100 crore rupees to build that campus. Why can't we try to do little more?
Sea change in 1 year.
No, you will see another sea change in coming 1 year. I hope so. Now it will be changed to positive. But you have a dream. You have good leadership. I think you can do it. And this is my concluding slide, that we owe our habitable planet from the photosynthetic world. We must nurture it properly to keep the balance of our atmosphere, so that our atmosphere do not go to toxic level, and our sea level changes are inevitable, but we are not promoting it. So with this, with a high hope to you all for your future, I conclude here. Thank you for your patient hearing.